Hi everyone, in the lab 5 we saw how we can build a deep learning model using the basic components like nonlinear activation functions, convolutional layers, and etc. and etc. We have compiled everything in NumPy as you can recall. This is good, but it would require you to calculate the gradients yourself in order to optimize all of this model and so on. So in this recording, as I promised you, I will show you an alternative way, which I believe can help you greatly in your next phases of your life, because probably you'll be training models and you'll be taking advantage from modern machine learning methods like deep learning and so on. I think it's beneficial for you to understand that there's an alternative. It comes with cool features like automatic differentiation, which means you don't have to calculate the gradients yourself. There is someone being the library itself will help you to calculate the gradients without you having to think about it. So let's start our journey. I will start a terminal, make it full screen, and I'll start with creating some directory. I'm creating a directory by this command mkdir space deep underscore learning. Okay, so let me go into this, and let's say we first want to build the model itself. Vim model.py could be a good base for our model. So there are things we want to import in order to achieve our task. I think this one of them is torch, and this is PyTorch, of course. Torch NN is another thing that you're going to find very useful. So I'm importing it as NN. And for now, I think this is what all we need. Let's start a class. Let's call this class as flexible model. Okay, and it's an NN module, as you can see from here. Of course, every class needs an initialization function. Self here refers to itself, this specific class. Always leave 2 spaces between different comments like this one. The things we need as an input to this class is we want to know how many channels our input has. Let's say n input is 1. Okay, that means I will give a data with a single input. Okay, and then another thing I want to know is how many channels my output has. Okay, that's also another thing. Now that I have it, since I'm building a very simple model, I think we can survive with these 2 inputs for now. But I think you can have many different inputs here, like how many layers, how many hidden channels, all these things that you have heard in the lectures. But let's keep it simple for now. Let's say super, and then we say flexible underscore model, and then self, and then underscore init underscore, and then we close the parentheses. Okay, the first thing I think we are going to do is to define some sort of model. And in order to do that, I will say there's this thing called layers, and it's a member of this class, and it's an n.sequential. There you go. And then you can have something like torch, or why do I say torch? You can say nn times nn.linear, and then you can say the input and output. And then I need a ReLU too. I will explain what I'm typing here in a second. Let's make it in place too, so that we don't suffer from okay, cool. So let's explain what you see here. I'm setting the numbers so that we can talk about this in the right way. Line 11 and 12, there is a linear layer. Okay, it's a linear layer. It's you can read about the documentation for this. And an easy way to learn more about each one of these things, you can go into any Python shell, anything you have, either Jupyter notebooks or a shell like this one, a terminal like this one, or IronPython, anything. Let's start with this IronPython because it uses color to highlight stuff. And then you can say import torch and then as nn, and then you can say help and then linear. This will get you directly to the documentation of this thing. Okay, as you can see, it follows this linear transformation to the incoming data, which is shown here. Okay, this is a completely linear model. Okay, now we learned this thing. We can press Q and exit this help and then type exit, and then we don't need this terminal for now, so I'm going to close the terminal on the right hand side, and by typing exits, now we have these sequential layers and so on. The second one is this ReLU, this nonlinear activation function. Okay, yeah, that's very strange modeling, to be fairly honest with you, because we have just one layer and an activation function. What typically happens is, like, you have a bunch of these layers followed by this nonlinear activation function, and then you have a last layer without any activation function, so that you can get negative numbers as well. As you can recall, ReLU is 0 on the negative side. If you provide a negative number to ReLU, it will give you 0. You remember this. Therefore, this always gets you a positive number. Okay. We build our model, to be honest, and the next thing we want to make sure is like how we use our model. I want to compile another definition function called forward, and I want to explain you why I need that. When we provide data, the data to this specific model here, we need to know how we are going to use these layers, right? We need to know that. And in order to know that, we need a function. And in my case, this function is forward function. And we can say y, which will be my output from this model, is equal to self layers. Oh, let's not do that. Maybe I can do like for layer in self layers. So that means I'm going to visit whatever this sequential has in it, one by one. So I will first visit this one, do something. I'll secondly visit this one, and then do something about this too. So we can say x is equal to layer x. Let's analyze what's happening here. Let me also return the result from this, return x. So we had x. We choose one layer from our sequential layers, and then we process that layer using the input x, and then we get this output x. Now we have a new updated x, and then we can go into this sequential model, choose the next one in line, and then process it accordingly and return it as well. So this is a model that just basically does that. So this is cool. One thing I do quite often when I code such models, I also do like def estimates. I write a function called estimation. I want to explain you why I do that. Return self forward x detach. As I told you guys, Torch is able to keep the graph as you process data. When you say detach, it just drops everything that it memorizes about this data that you provide, meaning it drops the graph and everything, drops the gradient and everything. So in the training, you'll be using this forward model. But once your model is trained, you need some sort of function that will help you to get the estimate you want from that forward model, and you don't want this to be, you know, like giving you also the gradients and causing lots of memory demands and so on. In order to avoid that, I just do this. This is just a simple reasoning behind this is that. So people do this in many different ways, but the way I do this is like I like to keep it inside this class. I will say we need a function called fit to train the model as well, or you can say like train. Maybe that's a better way to name this function. We need some input, let's call it x train, and then we need some corresponding ground truth output. This is y train, and we need to know how many steps, how many epochs we are going to take. Let's say 100. And as you guys well remember from all these other examples we have seen in the past, you need a hyperparameter called learning rate. And let's set that to some value here, as you can see. So next bit we want to make sure is that we have an optimizer. In the class we have seen gradient descent, stochastic gradient descent. I even give you guys some recordings, some tutorials live on like how you can code this gradient descent yourself, and you remember also the difference between gradient and stochastic gradient descent. All of these things you don't have to code from scratch. Torch gives you the right tools and lots of optimizers that are really efficient in the task you're going to assign to it. So I suggest you guys to use Torch's built-in optimizers. They are all gradient policy based optimizers. Let's call this self optimizer, and let's ask our Torch to give us one optimizer. I will be using Adam. Adam means this is some sort of stochastic gradient descent with a specific update rule. You may want to check a paper that is relevant to this thing, and I need to let me find this paper for you guys. Just give me a second. If we go into Google Scholar, and if I type things like let's say Adam optimizer, you will find lots of different versions of Adam optimizer, of course, but anything should do fine, I believe. Let me see if there's anything related to Torch. Oh, there is also this automatic differentiation in Torch paper. Do they also talk about this in here? Let me quickly check. Do they talk about Adam? There's a guy named Adam as one of these. Actually, two Adams here. Okay, let's see. No. Another way is to go into Torch documentation, Torch optim. Yeah, why are we doing it like this? We can just use the trick I just showed you guys. Let's go back into this IronPython, import Torch, and then I say help Torch optim dot Adam. If I do that, I should be seeing its documentation. Okay, does it refer to any paper? Yeah, look at this. For further details regarding the algorithm, we refer to Adam, a method of stochastic optimization. Okay, guys, we copy this. We go back to here. You go back to our Google Scholar and type this here to find the paper. As you can see, this is the paper with lots and lots of citations, like around 12K. This is because this is being heavily used in many of these deep learning models. They almost everyone is using these kind of optimizers. Of course, depending on your task, you may want to choose different optimizers. Yeah, this is the paper. If you're curious about the greater details, I think you should be consulting to this specific one. So I just wanted to let you know about this. Going back to this train function, let's close this because we don't need this on the right hand side. Exit and then exit. this train function, going back to that specific function, you have this self optimizer, and then we are assigning this Atom optimizer to be our optimizer. Of course, we'll be needing two things. One is we need to tell this optimizer what to optimize, and this is our optimization parameters. You can say optimizer parameters. Note that this is an NN module. Here, it just collects what is differentiable and then make it self.parameters. Okay. The second bit we need is the hyperparameter, the learning rate. How aggressively you will be changing your output, basically, depending on the error you're making in one single optimization step. You can say learning rate is equal to learning rate. As you can tell at the top, I set it to some other value here. Of course, we have this optimizer. Next thing we want to make sure is to find a way to penalize our steps, to find a way to say if we are doing a good job or a bad job. And that can happen with a loss function. Let me just create a loss function, self loss function. And Torch has lots of different various loss functions implemented. You can use like the very basic one, torch.nn.mse loss, and this will give you an mean squared error loss, L2 loss, basically. So you have all these things. Next thing you want to do is to just take steps and then update your model according to your data. And to do that, you need a for loop. You need to go through this entire data, and then you need to find out. The model parameters. So let's do this. For I in, or let's say for step in range. What was this? Okay, this is the epochs. Yeah, the epochs. We will take 100 steps here, right? If you recall my implementation from before about the gradient descent, we were always clearing the gradients at the start of each step. We will do the same here, self-optimizer.zeroGrad. Instead of assigning them to be 0, there is a built-in function called zeroGrad, which takes care of all these, all these things for us. It just clears the gradient. Next thing we want to do is to find out the estimate. Why estimate? Because our model will estimate some value as we provide the model the X train. So we will later compare this with our Y train to find out if our model is doing a good or a bad job in estimation. We can say self forward and then X train. See what happened here? You provided X train, you use this forward that we have compiled before, and you have some sort of estimate coming out of that. You have this now. Next bit you want to make sure is to calculate your loss to understand if you're doing a good job or a bad job. So let's do this. Self.loss function. We want to compare Y estimate with Y train, right? So we now also have an idea about if you're doing a good job or a bad job. The next bit is, as you can recall from this gradient calculation process, we were caring about the loss function and the model equation that we built at the time, right? So I think we were using a second order polynomial in that specific example. Here, we don't have to think about any of these, gradient calculations. This thing will think for us. And the way it does this is we take this loss, we say loss dot backward. I'm just doing this to be on the safe side. This retains the graph, and graph meaning this, all these gradient calculations and so on. So we now backpropagated the loss that we have calculated, which could also help us to update the model, which means our optimizer has to take a step right after this calculation. This is literally it. I mean, there's nothing more in terms of model building. As you can see, a few lines of code in PyTorch gets you a model Of course, you can augment this a little bit more. You can say like print, I don't know, like step, and then you can say comma, and then you can say loss here, and then you can say this format, and then you can say step, and then you can say loss dot item, because you don't want to just have the loss as a function being whatever comes out of this being just printed. You want the number, the one single number that tells you if your loss is high or low. Okay, I think I also need to close the parentheses here, and this is my model. This is my model. Let's train our model. Let's train our model, right? We need some data, some sort of data to train this model, to see if this is working or not. Let me also build a function called test, okay? In this test function, I'm just testing everything we have in this class. So first thing I need is xtrain and ytrain, some sort of data. I need those two. Let's define this xtrain real quick. Xtrain, ytrain, and then we can say like something like, I don't know, generate sample data. Let's create another function called generate sample data, and this generate sample data, it will generate x, and that is torch rand. It's some shape, right? Let's call it like, I don't know, size. Yes, hopefully this is not a restricted name. I can say size then. Y torch maybe random is a bad starting point, because let's fit a line. Let's fit a line. We can do something like yeah, maybe I don't need this, since this is just a test function. Maybe I can do like a range 10 or k. Let's call k as 10, and then I'll do the same for x, but I'll use some sort of yeah, let's start easy. Let's do this. M plus n, okay? M is 2, just some number, n is 10, and then I have return x, y. Hopefully you can follow this bit. I'm just generating some sample data, which is in the shape of this y is equal to mx time. Yeah, let's make this look slightly. Yeah. Okay, we have this right now. Okay, now we have this generate sample data. It's all there. It's just provided to us. Next bit we want to make sure is to generate a model from our model. We can say from using our flexible model. Remember, this non-linear could be also other things like COMP0088. Let me show you some stuff there. If I go into Python 3 again, import torch, and then I say torch nn dot com. Oh, I think I need to import torch nn 2, and then if I say torch nn dot let's see, nn dot com, it's here, right? No. Yeah, you can also use these other functions called torch COM2D or torch COM1D, one of them being one-dimensional convolution, the other one being two-dimensional convolution layer. I'm just using this linear model, but doesn't mean that you should always use linear model. Yeah, it's not a requirement or anything like that. It's just the coincidence that we are using this linear. You can use convolution. You can make convolution layers here if you want to. I just want to highlight that. Since our task is pretty simple here and approximates this case quite well, I think we can just survive with this test as is. Model is equal to flexible model. Remember, I need to provide this n input as 1 and n output as 1 too, because you know y is a single value coming out of this thing. Okay, next thing I want to make sure, after assigning this model, I want to train that model by model train, and then I can say I provide you x train, I provide the y train, and then I say do this for 10 epochs as a starter. Keep the learning rate as default. I will not assign it to be some value. Let's keep it as is. Or you know what, maybe in the future we want to play with it. I don't know what's going to happen next, so it's best if we just set this to some value for now. Okay. Model will be trained, and then we will be testing the model afterwards. If usually when you write a unit test, you can also do things like assert true is equal to true, I believe, if I remember correctly. Okay, let me quickly check. I want to check a quick sample that I coded for some other projects test. Yeah, you can do things like that. This way, you can use your testing routine in the library you will be creating in the right way. This is just telling your testing routines to, after this testing, it just provides a positive result. Basically, it's just saying that. Okay, so we have written all of these things, but if I go back to this other terminal and then I say Python 3 and then I say model, nothing will happen because I didn't tell what to do when this is triggered. I didn't tell, you know, which function to go in and follow and so on. So we can do test. Let's keep it super simple. Got an unexpected keyword. Adam didn't like my keyword. Let's see. I think instead of learning rate, I should have used LR, I believe. LR. But how do I know that, right? How do I know that I should have used LR? If I go back to this Python 3 again, import torch again, and then if I type help torch optim, if only I can type Adam, if I do this, you'll be left with this documentation, right? And if you look into these arguments here, it starts from here. These are the input arguments. LR is the learning rate. Default is 18e minus 3. Okay. That's how I knew it. And if let's start this one more time. Okay, this time another error. Let's see what's happening here. 10. Okay, I think I understand what's going on here. I want to try one thing before I explain this properly. Let me see. I want to check my notes real quick. Test. Okay, let's read this line and try to understand in one by one. Get this one. Do I? Let's see. What's the shape of this X train? And what's the shape of this Y train? It's 1 by 10, 1 by 10. Didn't like these shapes. Okay, let's see. Let me quickly check on this and then resume this instead of me trying multiple things. Just give me a second. Okay, I think I find the issue. I think there are two errors in this code. One of them is about the way we generate sample data. When I generate this like this, it just gives me 10 different values because k is set to 10. From 0 to 1, 0 to 10, I get these values. But what I need to be feeding into this is a shape like this, which means instead of having the shape of x as 10, it should be 10 by 1, okay? That's how it wants to operate. And then I do the same thing here. Another thing I should highlight is this model likes to work with floating numbers. Therefore, I have to, let's see this error together. If I type here Python 3 model, it will say expect a scalar type float but found long. We want this to be converted into float so that we work with the right type. That's another thing we need to be doing. But as you can see, the learning does not improve much at this point because of multiple different reasons. I think when I set these layers, I made one small mistake. I need to be doing self layers and n module list. This way, this specific class knows what to add to the parameters, self parameters. So I can then say new layer here maybe, and then I say I created this thing, and then I say like self layers append new layer. So let's try this one more time. Now you can see that it started to learn something, right? But still learning is too slow, right? I can either increase the number of steps I'm taking to see if I'm doing a better job. Started to decrease, the loss started to decrease, as you can tell here. Or I can take many steps here, but still not so good. Maybe I can be a little bit more aggressive with learning. I'm changing the learning rate. Now you can see that after 1,000 steps, I have a loss like this for the train. But the next thing we want to make sure to understand basically if this model is doing its job in the right way. Loss says it does. It learns quite well. It even says you don't need to take 1,000 steps, maybe 100 steps should be sufficient, right? Let's try that too real quick. I think maybe 200 is a better. What has happened? What did I change? Okay, if I make it 200, okay, maybe 500 steps. Okay, yeah, maybe 1,000 steps is a better option because we have a really small loss here. Okay, let's see if we generate some sample data, okay, for test. X test, Y test. Okay, we know this by heart, and then we can say like generate sample data. But instead of using k is equal to 10, I want to use k is equal to 5 to get numbers between 0 to 5, and they're going to just represent the first half of our is this a good approach? Maybe not. keep it k is equal to 10. K is equal to 10. Let's keep it like that. But I want to add here some sort of multiplier. Multiplier is 1. And I want to set this multiplier to be 0.1. When I do that, like, remember, k is from 0 to 10, right? All of a sudden, I get, if I set this multiplier to be 0.1, all of a sudden I get this 0, 0.1, 0.2, 0.3, and the last one will be 0.9, right? So I create a data that is not available. I mean, only the 0 is available in my train model, train data. Let's also print this, maybe to show that this is the case. Maybe printing it in here makes more sense. Print x train, let's say, and then I say x train, and then print y train, and then I say y train. Let's run this one more time. You can see, why did I, no, sorry, I wanted to do this x test, not train. Sorry for this, x test. Okay, guys, if I do this, you can see that in my original train set, I have 0 to 9. In my test set, I have 0.0 to 0.9. What I wonder is what happens, what kind of estimations are going to be provided for this simple test data, right? I can say, give me the estimate, y estimate is equal to model dot estimates, and then I say x test. Okay, I don't need to print these anymore because you guys have seen this already, and I want to know, I want to see what was the original ground truth data. I want to see that, and then I can say y test here, right? And I also want to see what my estimate looks like, right? And I can do that like this. Okay, I think this is a super good model. As you can see, like I provided these x test, and my test ground truth data is this. Like, these are the actual value that I should be expecting from my data. And according to my trained model, I got these values. You can try different kind of estimates as well. If you want to print, you can say, like, I don't know, like what model estimate, I don't know, like, let's say torch array, and then let's give it like, let's say if I'm curious about 5.5, let's say, or yeah, let's say I'm curious about that too, and I can say view -1 torch array, torch tensor, not array. Yeah, that was numpy. Yep. So we got 21, but how do we make sure if this is a good or a bad value? We can look into our train set and get an idea from that, because we know this is actually looking like this, right? Well, we can actually calculate this. Why not? We can say like print m is 2, right? In our model, in our data generation. And now we have this 5.5 plus n is equal to 10 in our model, in our data generation. We can also look into that to get an idea. As you can see, the estimate is 21, and the actual data should be 21 too. This means this is a great model. Our loss is also backing this up, and you can tell it from here. Okay, I will delete this line, and I will leave it here. But I just want to also highlight that anything you write in Python, any code you write, guys, please have this, as a part of your culture. Let's say in coding, you need to be providing descriptions. You need to be providing descriptions of what's happening for each one of these classes, functions, and so on. The reason for that, if you remember, I was going into this item Python and I was importing torch, and then I was saying like help, I don't know, torch tensor. Okay, when I do that, it reads this documentation mostly from here, from the things that you have written, you're going to write here as a doc strings. So this is a good practice in coding, in my opinion. Please have this. Don't write code that is, all around, like has no description and nobody understands it beside you, or maybe you yourself after like 4 days you forget about the code and then you return back, you don't remember anything about it. Don't do that. Please don't do that. Always write test routines. Try to provide notes within your code. I hate comments. I rather prefer correct documentation. So a good example here. This class is a flexible class for defining a model, a machine learning model in PyTorch. Okay, then you can do things like, another thing you can do here for the definitions, you can do things like initialization function, right? And then you can say parameters, and you can add this here. You can say n input, this is an integer, number of inputs, or the size of input, which will help define the shape of our first layer in our model. You can do things like that, and you can of course have like returns here if this function returns anything. Please do this kind of stuff because it will help you in the long term. Then it means that you write something, you write a code, and you can return back to that code after, if you like, 3 years, 5 years, whichever you like, and you'll still be able to make sense of it. That's very important. You'll see that it's super important. You'll use this feature in your life quite a lot in order to make myself, believable. Let's say, if you can say, why should we, follow your example here? I just want to give you one quick thing from my case. If you look into this is a library that I built. It's called ODAC, and this is on GitHub. You can subscribe to it if you like. It's up to you, of course. But you can see that there are these tests, and if you go into any of these functions, let's say, I don't know, learn, tools, loss, you'll see that the same feature is there. And why is this important? You can create good documentation out of this thing. If you click into this, you'll find out that there is documentation. If you click into here or learn tools, I generate all this automatically from my code. So this is a good feature to help you build meaningful documentation as well for other people. As you can see, we have provided parameters and returns. The source code is also shown here. types or explanations are also available here. So in my opinion, this is good practice. It helps other people to follow your example, okay guys? Then they can make sense of what you're doing, how you're doing it, and so on. I hope this was helpful to you guys. As promised, I will be sharing this video file, and I will also be sharing the code in the Moodle. And if you have any other further questions, we will see each other right after this reading week. Please take care, have fun during that time. Also, make sure to watch these lectures. It will be really, really important for your exams. I hope to see you soon. Bye.